Consider the mapping T goes from R to R, defined as T of x equals 7x, or alternatively, x gets mapped to 7x. So evaluate T of 2 plus 4, that is T of 6. So T of 6 is 7 times 6, which is 42. And then evaluate T of 2 plus T of 4. So T of 2 plus T of 4. T of 2, that's 7 times 2. T of 4 is 7 times 4, so that's 14 plus 28, which is, what do you know it, 42. Are answers to the previous two questions equal? Yes. Let's evaluate T of 3 times 5, or T of 15. So that's 7 times 15, which is 105. And then 3 times T of 5. 3 times T of 5, that's 3 times 7 times 5, which is 3 times 35, which is 105. Yes, answers are the same again. So what can we conclude about the transformation T? It is linear. The definition of a linear transformation is that T of A plus B equals T of A plus T of B, and T of C times A is C times T of A. Okay, so here's another mapping. T goes from R to R. T of x equals 3x minus 5. So T of 6, that's 3 times 6 minus 5. 18 minus 5 is 13. Okay, T of 2 plus T of 4. So T of 2, that's 3 times 2, which is 6, minus 5 is 1. And T of 4, 3 times 4 is 12, minus 5 is 7, 1 plus 7 is 8. Are those two answers equal? No. Okay, so what can we conclude about the transformation T? That it is not a linear transformation. Right? If it was a linear transformation, this question and this question would have the same answer. A quicker way to discover your conclusion from D that this is not a linear transformation would be to evaluate T of 0. So T of 0 is negative 5, which is not 0. Linear transformation, it's always true that T of 0 equals 0. So if you get T of 0 equals something that's not 0, it's not a linear transformation. Okay, why do you think we typically call the function f of x equals 3x minus 5 a linear function, even though it doesn't represent a linear transformation? And I think it's as simple as it looks like a line when you graph 3x minus 5. Okay, T of x equals ax, where A is the 1 by 3 matrix 0, 0, 1. Is T a linear transformation? Yes, because all matrix transformations are linear. And what is the domain of T? Okay, so T of x equals A times x. So the domain means what kind of x's can I plug in here? So the way I'm going to figure it out is I'm going to write out A, which is 0, 0, 1. And that is a 1 by 3 matrix, which means the next thing that I'm going to multiply it by, this x, has to be a 3 by something. Which means that my domain, the thing I can multiply by, is, and x is a vector, so this is x1, x2, x3. So the domain, the things I'm allowed to plug in are 3 entry vectors. My domain is R3. The codomain is the result after you multiply the 1 by 3 by the 3 by 1, you're going to get a 1 by 1 result. And those are your outputs, which is where the codomain is. So 1 by 1 is R1. It's just a real number that we're getting out. Okay, describe the action of t geometrically. I'm actually going to multiply 0, 0, 1 times an x1, x2, x3, and we get 0x1 plus 0x2 plus x3. So it maps every point in R3 to the x3 or the z-axis. What is the pre-image of 2? That is, what kind of vectors get mapped to 2? If I have 0, 0, 1, what kind of vectors do I multiply by to get 2? So this could be anything, and this could be anything, because you're going to multiply those both by zeros. But then this times this has to give me 2, so that has to be a 2. So if I were to write this in, say, set builder notation, it would be the set of all vectors x1, x2, 2, such that x1 and x2 are real numbers. What is the range of t? So my codomain is where the outputs live. So I've got 2, I've got x3. The question is, can you get any value in R as the output of this linear transformation? And yes, you can. You just have to choose x3 appropriately. So it is all of R is the range. Okay, number 4. Is T a linear transformation? Again, yes, because all matrix transformations are linear transformations. What is the domain of T? Well, if I'm set up a matrix multiplication, this is 2 rows, 3 columns, and then I have to multiply by a vector x that is going to have to be 3 by 1. Okay, so this is my domain, the set of all vectors that I'm allowed to multiply a by. So my domain is R3. What is the codomain? What do you get when you actually multiply these two things together? So if this is x1, x2, x3, then I have x1, and that's it. R. All the outputs live in R. Describe the action of T geometrically. Okay. Describe the action of T geometrically. So I'm going to actually multiply these out to see where I land. That's going to help me come up with what's happening. So when I multiply this times this, I get a 2 by 1 matrix. My first entry is x1, and my second entry is 0. So it maps vectors in R3 to the x-axis in R2. What is the pre-image of 1, 0? What kind of vectors get mapped to 1, 0? So I have 1, 0, 0, 0, 0, 0. What kind of vectors can I multiply by and get 1, 0? Okay, so this would have to be a 1. And then doesn't matter what x2 is, or x3, I will get 1, 0 no matter what those are. So the pre-image of 1, 0 is a vector that looks like 1, x2, x3. Okay, what is the range of t? The range is the set of all possible outputs, which all look like this. So the range is the set of all vectors that look like x1, 0, such that x1 is an element of R. And I messed up here at part C. The codomain, which is where things get mapped to, is R2. The resulting vectors after the multiplication all live in R2. Okay, in the coordinate system below, sketch the vectors u and v and their images under the transformation. Okay, so u is 1, 2, so I'll plot that. And v is -2, 4. It's right here. Okay, now their images under the transformation. T of u is going to be 3, 0, 0, 1 times 1, 2, which will come out to 3, 2. Okay, let's plot that one. Okay, then I also want to do t of v. V is -2, 4. So I do 3, 0, 0, 1 times -2, 4. And you get -6, 4. So what's happening is that my x coordinate is tripling. So this is a horizontal stretch by a factor of 3. Let t be a linear transformation. Suppose t of 0, 1 is 6 and t of 1, 0 is 4. Find the image of 2, 0, 1, 1, and 2, -5. So I'm going to use the fact that t of a plus b equals t of a plus t of b, and also t of c times a equals c times t of a. So I'm going to use that and the ability to build each of these vectors as a linear combination of these two. So 2, 0, t of 2, 0, that's t of 2 times 1, 0. And then this rule lets me pull the 2 out. So I have 2 times t of 1, 0. And t of 1, 0, I know it was given to be 4. So 2 times 4 is 8. T of 1, 1. That's t of 1, 0. Plus t of 0, 1. Which is 6 plus 4, which is 10. And finally, t of 2, -5. That is 2 times t of 1, 0 minus 5 times t of 0, 1. And I get 2, -5. What is the domain of t? The inputs for t, the transformation t, live in R2. What is the codomain? The outputs also live in R2. Is there a solution to each equation tx equals b? Yes, there is, because any vector can be written as a linear combination of 0, 1 and 1, 0. So, yes. What is the range of t? All the outputs, all of R2. We know that the range lives in R2 because the codomain is R2. The question is, do the outputs of the transformation t form all of R2? And the answer is yes. You can build any element of R2 by taking a linear combination of 1, 0 and 0, 1. Okay, t goes from R2 to R3 is defined by x1, x2 is equal to the absolute value of x1, the absolute value of x2 is 0. Is this linear? So hint, we want to check t of negative 1 times 2, 2, which is t of negative 2, negative 2. And according to this rule up here, the result should be 2, 2, 0. And then negative 1 times t of 2, 2. It's going to be negative 1 times the absolute value of x1 is 2, absolute value of x2 is 2, 0. All right, these two appear to be the same. I'm going to go out on a limb and say that yes, this is a linear transformation. Okay, quick fix here. This is not true because I forgot about this negative sign outside of my vector. So this comes out to negative 2, 0, and these two are not the same. So this is not a linear transformation.